Hi guys, can you guys hear me?
Yes, we can.
Okay. All right, so here's a quick announcement about exam 3 coming up next Tuesday. Um, exam 3 will consist of a little bit of later portion of chapter 17, chapter 19, and chapter 20, and that's it. Okay, so according to the syllabus, chapter 24 was supposed to be included exam 3, but then I decided not to uh, include chapter 24 in exam 3. So after exam 3, we're going to have two more classes, two more lectures, and about and we will quickly go over chapter 24, and that will be included in the final exam. Okay, so what I'm going to do is for chapter 24, I'm just going to go over the earlier portion of chapter 24. I'm going to focus more on the organic chemistry part than the biochemistry part. So biochemistry part will not be on the final exam. Only the organic portion will be included in the final exam. So the only new material that you have to study for the final exam is going to be the earlier portion of chapter 24. Okay, so again, exam 3 will consist of some of the later portion of chapter 17, chapter 19, and chapter 20. Okay, so up to whatever I cover this Thursday is going to be on exam 3.
Will there be a study guide, Dr. Lee?
Yeah, I will post a study guide sometime this week, and there will be no extra credit, no exam correction for exam 3. Okay, we're heading towards the end of the semester. I actually don't really have any time to grade those extra credit materials anymore. So exam 3 uh, we will not have any extra credit or any um, exam corrections available. So try your best to be well prepared for exam 3. Okay, my recommendations are the same. Create your own version of study guide, a thorough, very uh, detailed version of study guide, and then solve the sample exercises at least 3 times. Okay, everything on the exam will be anything that we covered during the class. So nothing new, nothing tricky, nothing crazy will be on the exam. Okay. Any question about exam 3? No? Okay. So last last Tuesday? Yeah.
Professor, sorry, I have a quick question.
Uh-huh.
Are you gonna post like the problems from chapter 17? Because the sample exercises at the end, they're
Mhm.
not done. I'm not sure if like we did them in class, but like it's not there, like the work for it.
Um I believe I replaced the file, but let me double check really quick.
Okay, thank you. Because the earlier portion of it is there, but it's just like the last few problems are not there.
Yeah, I thought I replaced the with the new PDF file, but let me double check.
Thank
When
you.
when was the last time you checked it?
Oh, I have it up right now.
Oh, so it's not updated?
No.
Okay, yeah, I'll change that.
Thank you.
Oh, okay. Okay. I'll do that after the class. So let's continue chapter 20. So we last time we stopped uh, at this slide. We learned about cell potentials. Okay, so the cell potential equation is this. Oops. Copy. Okay. So if you want to calculate cell potential, okay, standard cell potential of a cell, you take the reduction potential at the anode minus reduction potential at the cathode. Okay. So let's try a sample exercise using this equation. For the zinc copper voltaic cell, we have such and such equation, okay? And the standard cell potential is given. And then the standard reduction potential of zinc is given as negative 0.76 volts, okay? And they want you to calculate the reduction potential of the copper portion, okay? So we know that between zinc and copper voltaic cell, you know which one is the cathode, which one is the anode, right? So for the zinc here, the zinc and copper voltaic cell, zinc was at the anode, copper was at the cathode, okay? So okay, or we need to write this in the okay. So the reduction potential at the anode is going to be for this gaining of electron of zinc reaction. The reduction potential of the cathode is going to be gaining of electron of the copper. Okay, so the given information is standard cell potential and the reduction potential at the anode. Okay, so if we want to find the reduction potential at the cathode, we just have to basically rearrange this equation to find the reduction potential at the cathode, which is going to be minus. Oops. I think I put the wrong equation here. Give me 1 second, please. Zero 0.34. How come two equations are different? Give me 1 second, let me double check if the information I put on the slide is correct or not. cathode minus anode. Okay, I made a mistake on this slide over here. This slide 38. This should be cathode and anode. Okay, yeah. It should be cathode minus reduction potential at the anode. This is very important. I made a huge mistake. Okay. All right. So this is going to be cathode minus anode. Right. Okay. So since we have to find the reduction potential at the cathode, and now it makes sense. We will take the standard cell potential okay, minus the reduction potential at the anode. That gives us 1.10 volts minus 0.76 volts. Okay. That equals to 0.34 volts. So let's double check. Reduction potential of zinc 2 plus to zinc solid. Reduction potential of zinc 2 plus to zinc solid is negative 0.76 as given by the equation, as given by the question. And then the reduction potential of copper 2 plus gaining 2 electron, the potential of copper 2 plus gaining 2 electron becoming copper solid is positive 0.34. Okay, so that's how you calculate reduction potential at the cathode or reduction potential of the anode using this equation. Okay. Sorry about the confusion.
Can you go back to the last slide?
Go back to this one.
Yeah, please.
Let me know when you're done.
Okay, I'm good now. Thank you.
All right, let's try another sample exercise. Use table 20.1 to calculate standard cell potential for voltaic cell described in sample exercise 20.4, which is based on the reaction such and such. So I'm not going to scroll back because I don't want to freeze the screen, but in sample exercise 20.4, I'm not sure if you can recall, but we solved, we separated these reaction into half reactions. So the half reaction at the cathode was this portion. Okay, and then the half reaction at the anode was this. Solid, 60 electrons. Okay. And according to table 20.1, the reduction potential for dichromate to chromium is going to be positive 1.33. Okay, and then so this is a potential, the likelihood that dichromate to become reduced to chromium is measured to be positive 1.33 volts. Okay, and the reduction potential for the iodine I2 to gain electron and become I minus is going to be positive 5.4. Okay, so we know that from here, we know that the reduction potential of the cathode is positive 1.33. Reduction potential of the anode is positive 0.54. Okay, so the cell potential is going to be reduction potential of the cathode minus reduction potential of the anode. So 1.33 minus 0.54 volts equals to 0.79 volts. That's it. Let me know if I have to go back. Okay, we're going to try another exercise. A voltaic cell is based on two standard half reactions. Okay, half reaction, the cadmium and tin. Okay, use the data in Appendix E to determine which half reaction occurs at the cathode and which occurs at the anode. B, find the standard cell potential. Okay, so according to Appendix E, the reduction potential of cadmium to gain electron become cadmium solid is going to be negative 0.40 volts. The reduction potential of tin, okay, the likelihood of tin 2 plus to gain electron is negative 0.14 volts. Okay, so the standard reduction potential of tin is more positive than cadmium or less negative than cadmium. So the reduction of tin is the reaction that occurs at the cathode. Okay, and the reduction, the reaction of cadmium is going to be occur at the anode. Okay, so let's write that down. So cathode, you will have reduction reaction. At the anode, you will have oxidation reaction. Okay, why? Because difference in the reduction potential. All right, so now we determine what's at the anode, what's at the cathode. We can find the cell potential. Okay, it's going to be the reduction potential at the cathode minus reduction potential at the anode. So it's going to be negative 0.14 volts minus negative 0.40 volts equal to 0.26 volts. Okay, again, if you're working with a voltaic cell, the cell potential should always be positive. So if your math is giving you a negative value for a voltaic cell, you know that something is not right. Okay. So here is summary about reduction potential values. The more positive value of standard reduction potential value, the greater tendency for a substance to become reduced under standard conditions. Okay, greater tendency to gain electron. Okay, the more positive standard reduction potential value, the more likely that that substance is going to gain electron, greater ability to gain electron under standard conditions. The strongest oxidizing agent, okay, this oxidizing agent itself is going to be the one that is being reduced. This is the okay. So the oxidizing agent is the one that is being reduced, itself is being reduced. So the strongest oxidizing agent will have most positive reduction potentials. That makes sense, right? And as a reverse, the strongest reducing agent, the one that is being oxidized, will have the most negative reduction potentials. Okay, so here's a chart. Along the reduction potential list chart, okay, the left side, the left side of the reaction is showing gaining of electron process. As you see, the two electrons is gaining electron process. The reduction process is showing on the left side. The right side, if you put the arrow backward, okay, this side is showing, the right side is showing the losing of electron process, the oxidation process. Okay, the strongest oxidizing agent, the one that is being reduced, have the most positive reduction potentials. Okay, so with most positive reduction potential value, it is very, very easy to reduce fluorine, and fluorine would love to gain electrons, okay, and become F minus. But with less positive reduction value, it is very, very difficult to reduce lithium. Okay, lithium would not want to gain any electrons. It doesn't want to gain electrons. Okay, doesn't want to gain any electrons. And as for the oxidizing part, okay, the strongest reducing agent, the one that is being oxidized, have the most negative, okay, the most negative reduction potentials. Since reduction process of lithium positive has the least positive value, gaining of electron by lithium positive is very unlikely to happen, but the reverse is very, very, the oxidation, okay, oxidation process oxidation process by lithium solid is very, very likely to occur. Okay. So far we have observed that voltaic cell uses spontaneous redox reaction to produce positive cell potential or EMF. Okay. Okay. This is the how to calculate the EMF, how to calculate the cell potential, using the reduction potential at the anode minus the reduction potential at the cathode. Okay, so this is true for a voltaic cell. This is how you calculate the potential for a voltaic cell. And with the half cell potential, we were able to determine whether a given redox reaction is spontaneous or not, right? So from the cell potential equation of voltaic cell, we have a general equation for all redox reaction, and that is going to be this. Okay. So writing the equation in this way, the word cell over here is eliminated to indicate the calculated cell potential. Calculated EMF is not only for voltaic cells, but it is for all redox reactions in general. Okay, and instead of using term anode and cathode, we use reduction and oxidation terms instead. Okay, so again, this is for voltaic cell, but this is going to be used for the general all types of redox reactions. Okay, and when cell potential
That equation supposed to be cathode minus anode.
oh yeah, I copied the wrong equation again. Thank you so much. Oops. Okay, when cell potential is uh, not note that any cell, okay, not just voltaic cell, when cell potential is positive, this indicates spontaneous process. When it's negative, indicates non-spontaneous process. Okay, so that's same for voltaic cell, or that is true for voltaic cell or any type of cell that has a redox reaction. Okay, and um, the Gibbs energy, since Gibbs free energy is also the measure of spontaneity, right? If you can recall from the previous chapter. So the cell potential, okay, the cell potential and Gibbs free energy they're related. Okay, the relationship between cell potential and Gibbs energy, Gibbs free energy, is explained by this equation over here. Okay, the letter F is the Faraday's constant, named after Michael Faraday. Okay, N is the number of moles of electrons transferred during a redox reaction. Okay, so the Faraday's constant here is the unit is in coulomb per mole, but you can also have unit of joule per volts mole. Okay, please take a note. Okay, so because the delta G naught standard Gibbs free energy is related to the equilibrium constant K, this entire diagram shows how different expressions of the standard Gibbs free energy and standard redox cell potential is all related. Okay, don't forget that for Gibbs energy, negative value indicates spontaneous process. Positive value indicates non-spontaneous process. Okay, so okay, if you can recall, this is from the previous chapter. Okay, and this relationship is what we just learned. Okay, let's try a sample exercise using the equation that we just learned. Okay. Use the standard reduction potentials in table 20.1 to calculate the standard free energy change delta G naught and the equilibrium constant K at 298 Kelvin for this reaction. Okay, and question B, suppose the reaction in part A is written uh, as such, what are the values of standard cell potential, standard Gibbs free energy, and equilibrium constant when the reaction is written in this way? Okay, so basically question B, everything is multiplied by 1.5. So the reaction is halved. Okay, so we have to calculate these three parameters when the reaction is halved. Okay, let's try question A first. So for question A, we are given standard reduction potential values from 20.1 and are asked to calculate the standard free energy change and the equilibrium constant. Okay. First, we need to determine which is the reduction part, which is one is the oxidation part within this redox reaction. Okay, so let's do that first. The reduction part is going to be this. Gaining of electron. Okay. Oxidation part of the reaction is going to be this part. Okay. And then according to this table over here, let's try the reduction potential for this portion. Okay. The reduction potential is going to be positive 1.23. And for this reduction potential for the oxidation reaction, okay, for silver to gain electron is going to be 0.80. Okay. Volts. All right, so now that we have reduction potential for reduction and oxidation, we just have to calculate the standard cell potential. That's going to be 1.23 volts minus 0.80 volts, 0.43 volts. Okay, and we're going to use the equation that we just learned, the relationship between Gibbs free energy and the standard cell potential to find the standard Gibbs free energy. Okay, so delta G naught equals to negative N Faraday's constant standard cell potential. Okay, so the delta G is going to be negative. N is the number of electrons transferred. 4 electrons were transferred, okay, during this redox reaction. So we're going to just put 4. Faraday's constant, 96485 joule per volts mole times standard cell potential is calculated to be 0.43 volts. Okay, so that gives us negative 1.7 times 10 to the 5 joule per mole. You can keep this way, or you can also do negative 170 kilojoule per mole. Okay, it doesn't really matter. They're the same thing. All right, so now that we have delta G naught calculated, we can simply use this equation to calculate the equilibrium constant K. Delta G naught equals to negative RT natural log K. This is the equation that we learned in previous chapter. Natural log of K is going to be delta G naught divided by negative RT. Okay, the K, equilibrium constant K, is going to be e to the delta G naught divided by negative RT. Okay, that's equal to e to the negative delta G naught is calculated to be negative 1.7 times 10 to the 5 joule per mole divided by R is the gas constant, 8.314 joule per Kelvin mole, okay, times 298 Kelvin. The temperature was given. Okay, if you do this math, you will get 6.3 times 10 to the 29. Okay, that's going to be the equilibrium constant. So question A, all the required information is already found. So that we found the del standard free energy change and the equilibrium constant K. For B, since I don't have much time, actually I can go over. Okay, so for the second part, the part B, the reaction is multiplied by 1.5. Okay, so the question is asking for a situation when the reaction is multiplied by, the reaction is halved. Okay, in this case, we know that standard cell potential is an intensive property. I explained this during last class. So the standard cell potential value won't be affected. Okay, so these values over here, they are not affected by the reaction, the quotient in the balance equation. The reaction stoichiometry has nothing to do with these cell potentials. Cell potential is an intensive property. Okay, so this E cell standard cell potential that we found, it's just going to be 0.43 because it won't be affected by the reaction stoichiometry. Okay, however, as you can see here, delta G is affected by the number of electron transferred. But as you can see, if you have the reaction, the number of electron transfer is going to be reduced. The number of electrons going transferred during this redox reaction is going to be reduced. So we know approximately that the delta G value is going to be reduced, or it's going to be have different n value, and therefore, if the Gibbs free and standard Gibbs free energy have different value, the equilibrium constant K will also be affected. So question B, we're going to write this down. Since standard cell potential intensive property the standard cell potential is not affected by reaction stoichiometry. Okay, so the cell potential is still going to be 0.43 volts. Okay, now delta G naught is going to be negative 2 times 96485 joule per volt mole times 0.43 volts equals to that equals to negative 8.3 times 10 to the 4 joule per mole. And then if we plug different delta G value to calculate the equilibrium constant, that is negative 8.3 times 10 to the 4 joule per mole divided by negative 8.314 joule per Kelvin per mole times 298 Kelvin equals to 7.94 times 10 to the 14. Okay. Let me know if anybody need more time for this slide. Okay, so far we have been observing Gibbs free energy under standard condition denoted by delta G not over here. Okay, but I'm not if you can recall from chapter 19, we were able to calculate Gibbs free energy under non-standard conditions. Okay, so the equation what to find Gibbs energy at non-standard equation was this. Okay, this equation is from thermodynamics. Okay, so since delta G naught is NF E naught, okay, the delta G is going to be NF E. Okay, so this is a standard condition, non-standard condition. Okay, if we divide both sides by negative NF, if we divide both sides by negative NF, we get this expression. This is called Nernst equation. Okay, and since it is customary to express the Nernst equation in terms of base 10 logarithm, we're going to change natural log to log. Okay. So if you're wondering where did this 2.303 comes from, natural log of x equals to 2.303 log x. Okay, so we like to express in terms of log. Okay, and at 298 Kelvin, most of the time the electrochemical reactions are run at standard temperature. Okay, so at 298 Kelvin, the equation becomes like this. Okay, so this temperature, okay, temperature in this portion will give you this equation. Okay, and then you remove the gas constant and Faraday's constant, you get this number. And this is going to be the common Nernst equation that you are going to use throughout this chapter. Okay, and this is what you want to memorize. If you wonder what the Q is, this is basically going to be the reaction quotient Q. Okay, so using this, we are able to calculate cell potential at non-standard conditions using the standard conditions cell potential value. Okay, let's try a sample exercise. Calculate the EMF, the cell potential at 298 Kelvin generated by voltaic cell in which the reaction is, this is a reaction that we already saw multiple times, when the concentrations are given. Okay. Note that the concentrations are not 1 molar. This is obviously a non-standard condition. So we will have to use the Nernst equation to find the cell potential of this reaction. Okay. So from sample exercise 20.6, this equation, okay, from sample exercise 20.6, we already calculated the standard cell potential for this redox reaction to be positive 0.79 volts. Okay, so I'm just going to transfer the information here. And we have already figured out the half reactions and found out the number of electrons transferred within this reaction. I'm going to quickly write that down. Okay, and then this is the Nernst equation. Okay. Since we know the standard cell potential value and we know the N value, the only parameter we need to find is the reaction quotient Q in order to find the cell potential at non-standard condition. Okay, so the reaction quotient is basically product concentration divided by reactant concentration. Okay, don't forget to raise to the power equal to the coefficient. Okay, so as for the product, we have chromium 3 plus raised to the power of 2. Iodine is solid, water is liquid. We're not going to include these. Pure solid, pure liquid. Okay. As for the reactant part, we have Cr2O7 raised to the power of 1, okay, times proton concentration. Okay. So that is 1 molar. Nope. Raised to the power of 14. Okay. And then I minus raised to the power of 6. So let's plug in all this information. Okay. Plug in all the values provided. 1.0 times 10 to the negative 5 square divided by 2, 1 raised to the power of 14, 1 raised to the power of 6. That gives us reaction quotient value of 5.0 times 10 to the negative 11. Okay, so now we have all the values that we need to plug into this Nernst equation. So the cell potential at non-standard condition is going to be cell potential at standard condition, which is 0.79 volts, minus 0.0592 divided by number of electrons transferred during this process was 6 electrons. 6 electrons were gained and lost. Okay, so 6 times log of 5.0 times 10 to the negative 11. That gives the cell potential value of 0.89 volts. Okay, so this is how we use Nernst equation to find cell potential at non-standard condition using the standard cell potential value. Okay. Let's try another sample exercise. Let me know if I have to go back. All right, so this is a zinc hydrogen cell, okay, that we have observed before, which has a cell reaction that looks like this. And then we have previously found that the standard cell potential of the zinc hydrogen cell is positive 0.76. Okay, so the standard cell potential was previously found to be positive 0.76 volts. Okay, so the question is saying that the potential of this cell is 0.45 volts. So definitely this tells us that this cell is not at standard condition, because if it was under standard condition, it would have it would have potential of 0.76. Okay, so this tells us that this cell is at non-standard condition. Okay, and it's given the concentration of zinc to be 1 molar, the partial pressure of hydrogen gas to be 1 atmospheric pressure. And it's asking for the pH of the cathode solution. So pH of the cathode basically means proton concentration. It's basically asking for this proton concentration. Okay. So the question is asking us to find proton concentration at non-standard condition. Okay, when the cell potential is other than 0.76 volts. So we will again use Nernst equation to solve this problem. Using the Nernst equation, we can solve for reaction quotient Q. Okay? And the reaction quotient Q should provide us information regarding this proton concentration. And then we can find the pH value. Okay? So let's write out the expression for reaction quotient Q first. The reaction quotient Q is basically zinc concentration raised to the power of 1 times partial pressure of hydrogen, okay, divided by zinc is solid, so we're not going to include proton concentration raised to the power of 2. This is the expression for reaction quotient Q. So if we can find Q, and if we have all of these information, we can easily find the proton concentration. And proton concentration is basically the pH value of the solution. Okay, so let's find the Q value first. So if we solve for Q, you will get, if you plug in all the information and solve for Q, you will get 3 times 10 to the 10. Okay, so now we know that the three times 10 to the negative 10 to the power of 10 equals to zinc concentration times partial pressure of hydrogen divided by proton concentration squared. Since we know these values, let's plug in that information. Or if we, let's solve for proton concentration. This is going to be zinc concentration, which is 1 molar, okay, times partial pressure of hydrogen is 1, okay, divided by 3 times 10 to the 10 equals to 3 times 10 to the negative 11. If we solve for proton concentration, we need to square this value equals to 6 times 10 to the negative 6 molar. Now that we have proton concentration, we're going to, now it's easy to find the pH of this solution. It's basically negative log of the proton concentration. Which is equal to 5.2. So the pH of the solution is 5.2. The concentration of hydrogen in this zinc hydrogen cell that produces 0.45 volts of cell potential, the concentration of hydrogen is going to be 6 times 10 to the negative 6 molar.
Professor,
Uh-huh.
how did you get 1 times 1?
So I plug in the zinc concentration, 1 molar, and then partial pressure of hydrogen, 1 atmospheric pressure.
I see it now. Thank you.
Where did you get Q is 3 times 10 to the 10?
This one, you have to solve it. But I just don't have enough space and I don't have time, so I didn't do all the math. But it's just basically you plug in all the information. So you have this value here, 0.45, plug that in. The standard cell potential is given as 0.76, right? Okay, plug that in. The number of electron transfer is basically 2 electrons, right? Plug that in. You solve for Q.
Got it, thanks.
All right, let me know when you guys are done. Okay. So far we looked at cells that operate through 2 different substances differ in reduction potential, right? So we typically had zinc here, hydrogen here, or zinc here, copper here. We've looked at cells that operate through 2 different substances at the anode and cathode. But cell EMF or cell potential actually highly depends on the concentration Okay, let me know if you can't see the screen that I'm sharing, okay? So cell EMF or cell potential is depend on concentration. So a voltaic cell can be designed using the same species in both half cells just by fluctuating the concentrations. Okay, so a cell based on cell potential generated due to difference in concentration is called concentration cells. Okay, so for example, the diagram here is showing concentration cell created from different concentration of nickels. Okay, so in the left half cell, the cell has nickel metal in submerged in 1 times 10 to negative 3 molar of nickel 2 plus solution. The other half cell, the right side of the half cell, also has nickel metal sticking in here. So the both anode and cathode has nickel, right? Metal. But the solution has different concentration. The solution over here has concentration of 1 molar of nickel 2 plus solution. Okay, so due to this difference in concentration, the voltaic cell operates and the electron they transfer. The voltaic cell will operate until the concentration in both cells equal to each other and the reduction will be stopped. Okay, the transfer of electron is no longer possible when the concentration is same. Okay, so the concentration cell is basically a cell based on potential generated due to difference in concentration. Okay, so the difference in concentration is the key part. The eel is showing here is because eel tends to create voltage through this through the concentration cells. Okay, so for example, different concentration of sodium or different concentration of potassium, for example, will create this voltaic cell within eel. Okay, to create electricity, and that's why eel creates voltage. Okay, through the concentration cell model. So, since the anode and cathode within the concentration cell, since the anode and cathode both consist of same substance, the reduction potential at the anode and cathode, the reduction potential at the reduction site and oxidation site should be equal, right? Since you have same materials on both cathode and anode, this standard cell potential is going to be 0. However, although the standard cell potential is 0, the cell potential is not going to be 0 if there is difference in concentrations. Okay, if the reaction quotient Q value is not 0, okay, then the cell will operate. Okay, according to this Nernst equation, as long as concentrations are different, as long as reaction quotient Q is different, there will be cell potential generated, even though the standard cell potential is 0. Okay, so that's all I have for today. I'm going to hang around for another five minutes, just in case anybody else has questions. On Thursday, I will cover rest of chapter 19, and next Tuesday is going to be our exam 3. Okay, exam 3, same thing. The exam is going to be about 33 to 35 multiple choice questions. it's going to be 1 hour 15 minutes long. Okay, 1 hour 15 minutes long. Some people have talked to me about uh, the the clock, the timer within the lockdown browser. They said it's hard to see because they have to scroll up all the way to the top. So in that case, if it's too hard to see, you can prepare your own clock or watch that are not digital. Okay, so no Apple Watch, no digital watch, no Android watch, okay, no iPad, no phone. Okay, you can have a like a physical clock on the wall, or you can wear a non-digital watch on your wrist, or you can put it next to you on the table to track your time. That's totally fine. Okay, so if you want, you can prepare your own clock and watch before the exam. Okay. Otherwise, okay, I've talked to the OIT. That's the best they can do. You have to scroll up all the way up to see the timer for the exam. Okay, but if that's inconvenient to you, I'm giving you option to prepare a clock or a watch. So if you are staring up on the wall to see the clock on the wall, that's fine. As long as your face is not completely away from the camera, that's totally acceptable. Okay, and if you're wearing a watch on your wrist, if you're looking down to watch your watch on your wrist, that's fine too, as long as your face is not completely away from the camera. Again, no Apple Watch, no digital watch, no phone. Okay, do not use your phone to track your time. No iPad. Okay, no tablet. Okay, no digital source for to track your exam time. Okay.
Professor,
Yeah.
I have a question regarding slide 43.
Slide 43. Okay.
So, for example, one of the nurse equations says cathode minus anode, but then on this page you did the opposite. How do you know when to use cathode minus anode and then anode minus cathode?
Here, didn't I use cathode minus anode?
Well, isn't it? I'm not sure
It's
if I'm confused.
it's cathode minus anode. So I made a mistake earlier. I put anode minus cathode. This is incorrect. Please correct this.
Okay, I was just confused because since it says anode and then it says CD, and then the
Where?
value of, so on page 43, so cadmium is in the anode equation, but then we did 14 instead of 0.4.
So cathode minus anode is what I did. Cathode minus anode. Can you see that?
Yeah, I was just confused because of the E naught reduction on the top.
Yeah,
You
you're
see,
finding reduction potential for both. So for both, you need to find the reduction potential. So this is the reaction occurring at the cathode. This is the reaction occurring at the anode. For both, you need to find the reduction potential.
okay, and you did cathode minus anode. Oh, okay, I'm sorry.
Yeah.
I'm just so over the place.
Yeah. Okay, so determine the reaction occurring at the cathode, determine the reaction occurring at the anode, but for both cathode and anode reaction, you need to find the reduction potential. So you are trying to determine who's going to win the electron war. Does that make sense? Yeah, the reduction potential basically tells you who has stronger pull for electron. That's why you need to find the reduction potential for both reaction occurring at the cathode, reaction occurring at the anode. Okay, so whatever has more positive reduction potential value, that means that reaction has that specific substance has stronger pull for electrons, so it's going to win the electron war, right? So then the electron is going to be electron is going to be transferred to tin 2 plus rather than electron transferred to cadmium 2 plus. Does that make sense?
Yeah, so
Yeah.
if the electrons are on the left side of the equation, that's how we know it's a cathode.
Electrons are on the left side of the equation. Yeah, so whatever is gaining electron, then that's cathode, right?
Mm-hmm.
Yeah, so and whatever losing electron, if your oxidation is occurring at the anode, reduction is occurring at the cathode, right? So go back to the voltaic cell diagram and you will have better understanding. So again, oxidation always occurs at the anode, reduction always occurs at the cathode. Okay?
Okay, and then one more question about that slide.
Yeah.
So for the anode, why did you flip the equation?
For anode, why did I flip the equation? For this one?
Yes.
So anode is what? What occurs at the anode?
It
Oxidation
is,
or reduction?
I think it's reduction.
No, anode oxidation occurs at the anode, right?
Okay.
Yeah. So if there were oxidation reduction reaction, this is going to be the oxidation part, this is going to be the reduction part, right? So cadmium solid has to lose 2 electrons that will be transferred to the cathode, and then this tin 2 plus is going to accept the 2 electrons transfer from the anode, right?
I'm sorry, I got confused.
Okay, so here's the anode. Here's the cathode. Okay, so at the anode, cadmium is going to give up 2 electrons. Okay, and then that electron is going to get transferred to the cathode, right? And then who's going to receive that 2 electrons? The tin 2 plus is going to receive that electrons. This is the oxidation reduction reaction. Someone has to lose electron and someone has to gain that electron. Does it make sense?
Yeah, so did you flip the equation because of the values that they had?
I didn't flip the equation. This is the oxidation reaction. For the oxidation reaction, you will lose electrons. So electrons should be on the right side of the equation.
Right, but
Yeah.
when it says
So here, what is this showing? Is this showing oxidation and reduction, or only reduction?
only oxidation, I mean reduction.
Reduction, right?
Yes.
But in order for a voltaic cell to operate, can both be reduced? No. One has to be reduced, one has to be oxidized, right? So this question, they wanted you to determine which one is going to be oxidized, which one is going to be reduced.
Mm-hmm.
Do you understand that part?
Yes.
Yeah. So that's why, because looking at the reduction potential, it looks like who has stronger pull for electron? It looks like tin has stronger pull for electrons. So we know immediately that tin is going to steal the electron from cadmium, right? So the cadmium will be oxidized. It will lose 2 electrons, and that electron is going to be gained by tin. Let me put this up here.
So basically, if the E naught reduction is less, so like not closer to 0, but less than 0, then it has the strongest pull for electrons.
What's that again? One more time.
If the E naught reduction value,
the reduction potential,
yeah, it's very low, then we know that, oh no, the opposite. If it's closer to 0, then we know that it has a stronger pull for electrons. So that's why it would be the reduction equation.
Okay, so write this down. More positive reduction potential has higher pull for electron. Okay, write this down. More positive reduction potential value will have stronger pull for electron. Okay? So here, do you see the reduction potential values over here?
Yes.
Yeah, along this table, which one has the most positive value? This, right? Fluorine.
Correct.
This tells us that fluorine has strongest pull for electrons than any other substance listed below it. Okay? So more positive reduction potential value tells us that it has stronger pull for, it's greedier for electron, it's more hungry for electron. Does that make sense?
It does. So
Yeah.
basically, if we were comparing fluorine and lithium in that chart, lithium would be the oxidation equation or the anode, and then fluorine would be the reduction or cathode.
I mean, if you were designing a voltaic cell using these two substances, yes, that's correct.
Okay.
But just by looking at this table, the only thing you can tell is that fluorine has stronger pull for electron. Lithium positive has very low pull for electron. That's all you can say from this table. Okay? But if you were to design a cell, let's say, how about let's design a cell between fluorine and hydrogen. Okay, which one is going to be reduced? Which one is going to be at the cathode? Which one is going to be at the anode?
Fluorine would be the cathode.
Correct. And then hydrogen is going to be at the anode, right?
Mm-hmm.
So yeah, you got it.
Okay, thank you so much.
So I didn't flip the equation. This is the right way to express the oxidation equation at the anode. Okay.
Yeah, that makes sense. Thank you. Oh, and one more question. So the voltaic values that you got for cadmium and SN, those were grabbed from the table that we were looking at, right?
This is Appendix E.
Okay.
Yeah.
And then will you provide the values for
Yes.
us during the exam?
Of
Okay.
course, yeah.
All right, thank you.